Hello, Royals. You may have noticed on our outline that there is no lesson 5.2. 5.2 used to be evaluating trig limits, and it's not really in our curriculum anymore. Some teachers used to think that it was useful, and it is kind of interesting, but it is totally optional as well. The problem is that by not having that lesson, we no longer have a proof for our two most important trig derivatives, the derivative of the sine function and the derivative of the cosine function. So I want you to see a proof of that. You are not required to reproduce this. In lesson 5.3, you'll see at the top a faster version of this that doesn't use a robust proof. It just asks you to sketch things or to substitute in small values of h to evaluate a limit, almost like an advanced functions student would. But yeah, this is one of the most interesting proofs that we have access to in this course, but you are not required to be able to reproduce it. Okay, so our goal is to find an expression for the derivative of the sine of x. And what we do, the first time we deal with a new function, anytime we deal with a new function and we're trying to differentiate, we go back to first principles. We use a limit. So here's the first principles definition. F prime of x is going to be the limit as h approaches 0 of our difference quotient, f of x plus h minus f of x all over h. Let's get more specific. I substitute in the specific expression. I get sine of x plus h minus sine of x all over h. Now this is where I wanted you to just review the sine sum formula. I don't think you'll have an opportunity to use the sine sum formula, but it's nice to know it because it's required for this proof. To deal with the sine of x plus h, this is in an indeterminate form. I don't know how I'm going to find a factor. I don't think I can rationalize. Variable substitution doesn't look like a good option. I kind of have to use some trig properties. So here's the sine sum formula. Sine of the first, cosine of the second, plus cosine of the first, sine of the second, minus sine of h. Okay. What I notice is that there is a common factor here of the sine of x. So I believe this is some rearranging and removing a common factor, and then that term ends up right there. And what I'm looking for is two smaller limits and to remove some constants. So I'm actually using limit properties here. The sine of x is constant as h changes. There's a big sum here, so I'm going to use the limit of a sum property and a constant multiple property on the same step. I know, luckily I wasn't asked to show all steps, but it's a proof. You should be showing all steps. I should be showing all steps. So yeah, here we are. We have the sine of x. The expression for the derivative is going to be the sine of x multiplied by this limit here. The limit as h approaches 0 of the cosine of h minus 1 all over h, plus the cosine of x multiplied by this limit right here. The limit as h approaches 0 of the sine of h over h. And both of these are in an indeterminate form. So this now becomes my goal. I'm going to focus on this limit right here. And it's a really interesting proof called a squeeze theorem. It's a popular approach for other proofs. The way a squeeze theorem works is that if I can prove that this limit is going to be between two numbers, then I can sort of squeeze those numbers together and try to find the value of the limit. So to do that, I draw an angle H here. So the angle H is the angle EOB. I've got a circle with a radius of OD that's equal to OC. From the point where my terminal arm, OE, crosses the circle at C, I drop altitude down and create another point B. So the argument here goes that the area of triangle OCD, I feel like I didn't write that well enough. That's still not good enough for me. Jokes. Area of triangle OCD has to be less than the area of this sector OCD. The area of the sector is like the slice of that circle there. And that area of the sector has to be less than or equal to the area of triangle OED. Okay? Now we've just got a little bit of rearranging to do. In the triangle OCD, side length BC is going to be given by the sine of h. You can say sine of h is that length divided by that radius. I've just rearranged right there. Oh, did we make? Yeah, sorry. This is a unit circle. It's of radius 1. That's why you don't see the 1 there. That helps me build a formula for the area of the triangle OCD. It turns out to be the sine of h divided by 2. The area of a sector of a circle is just going to be proportional to the area of the circle. There's the area of the circle. And it's multiplied by what fraction of the 1 full rotation we've gone through. So since 1 full rotation is 2 pi, and we've gone through a rotation of h, this area of the sector of that slice of pi is going to be, slice of cake, shouldn't use pi, slice of the circle, is going to be h2 piths as big as the area of the entire circle. So I can simplify that down to r squared times h divided by 2. But, like I forgot before, the radius is going to be 1. That just simplifies things a lot. So the area of the sector is actually h divided by 2. We don't do a ton of circle geometry in high school math anymore. Actually, there's a little bit of it in the grade 12 college course, college for technic, or math for college tech. In triangle OED, to get to the expression ED, it's going to be given by the tangent of h. I'm just using the ratio of the opposite to the adjacent there, with an adjacent side of 1. That means that the area of triangle OED is the tangent of h divided by 2. Okay. Now, I split this, call it like a triple inequality, into just 2 separate inequalities. And I substitute this information here. The area of triangle OCD has to be less than the area of the sector, less than or equal to, sorry, we're talking about in the borderline case, if h is 0, those areas would all be equal to each other. They'd be equal to 0. So I've got the sine of h divided by 2 is less than or equal to h over 2. I rearrange here and I get that the sine of h divided by h has to be less than or equal to 1. This is important because I'm looking at what the limit as h approaches 0 of the sine of h divided by h is. It has to be less than or equal to 1. The area of the sector has to be less than the area of that larger triangle. I substitute in the information from above in here. That means that h divided by 2 has to be less than or equal to the tangent of h divided by 2. I rearrange here and get that h has to be less than the sine of h divided by the cosine of h, or the cosine of h has to be less than the sine of h over h. It's a little bit of tricky rearrangement. I called this statement statement number 1 and this statement statement number 2. Let's combine those statements. And I get that the cosine of h has to be less than or equal to the sine of h divided by h, which has to be less than or equal to 1. Now my goal was to find the value of, sorry, as I move around here, the limiting value as h approaches 0 of this ratio. So let's make it a limit. Where are we? We're right here. This means that the limit as h approaches 0 of the cosine of h is less than or equal to the limit as h approaches 0 of the sine of h divided by h. That's my goal, which has to be less than or equal to the limit as h approaches 0 of 1. Fine. Now, the limit as h approaches 0 of the cosine of h, well, this is determinate in this form. So the value of that limit is 1. So this expression that we're looking for, the limit as h approaches 0 of the sine of h divided by h, we've managed to squeeze the right-hand side and the left-hand side together and say it has to be some number that is greater than or equal to 1 and also less than or equal to 1. And that means that there is only one possible answer for the limit as h approaches 0 of the sine of h over h. It must be 1. This is one of my favorite proofs. I really wish we could have done it in person. To find an expression for the other limit that was required in my derivative, I do a little bit of rearrangement. I'm multiplying by the conjugate here to build a difference of squares so that I can use a Pythagorean identity to rearrange. I use a constant multiple rule. I use limit of a product rule. I've already determined the value of that limit. And then this limit turns out to be in a determinate form. So the value of that limit is going to be 0. So all the way back, again, sorry for the shakiness here. Put those 2 pieces of information into here. The value of this is 0. The value of this is 1. And we get f prime of x is going to be the sine of x multiplied by 0 plus the cosine of x multiplied by 1, which is the cosine of x. That is the punchline, and it's quite a short punchline. You need to know that the derivative of the sine function is the cosine function. And you can tell this from a sketch. I mean, you would have hypothesized this from a sketch. Maybe you weren't convinced that the greatest rate of change is also going to be 1. But here's the sine function. Its derivative function is going to begin with a maximum, have a maximum on the y-axis, then fall to an axis of 0 or root of 0, fall to some minimum, back to some axis, and then climb to some maximum, just like a cosine curve. Now here's a fast little proof for finding the derivative of the cosine curve. You could visualize it and see come up with a hypothesis, but what I'm going to do is use another one of our old identities from advanced functions. I've got some second function g of x being a cosine function. I'm just going to use the cofunction identity. Cofunction identity doesn't got a lot of love. It's not that useful in proving a lot of identities. It tends to just, if you use the cofunction identity and then use the sign difference formula, it just loops right back onto itself in a bit of a face palm move. But here it's useful because I know what the derivative of the sine of something is. To take g prime of x, I just need to use a chain rule. It's going to be the derivative of the sine of something, which I just spent, I don't know, I didn't start a timer, a while proving is going to be the cosine of something, and I just need to multiply that by the derivative of that inside. The derivative of pi by 2 minus x is -1. Okay. So yeah, fast version of 5.2 then is that the derivative of the sine function is the cosine function, and the derivative of the cosine function is the opposite of the sine function. In lesson 5.3, you're just going to practice using those two new derivative skills and use them with the product rule and the quotient rule and the chain rule and even some implicit differentiation. So have fun.